Good evening, sir.
Good evening. Good evening, everyone.
Good evening, sir.
Good evening, Deepak. Good evening, Jagdish, Neetu. Good evening. Good evening, Sachin. All right, so I was discussing, is my audio clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so I was discussing fluid mechanics yesterday. We talked about some definitions of various kinds of fluid flows. I talked about the continuity equation. I talked about the Euler's equation of motion. I also talked about the Bernoulli's equation. All right. There are various questions that have come mostly that is focused on either the continuity equation and most of the time Bernoulli's equation. So let us discuss the Bernoulli's equation a little bit in detail and then we'll start doing some problem solving. Okay, so I derived in fact the Euler's equation of motion. Okay, it's simply said that these individual terms, which is the change in the pressure upon the density of the liquid plus g acceleration due to gravity multiplied by the change in the vertical height and velocity times the change in the velocity is equal to 0. So this is the Euler's equation that I derived yesterday, and using the Euler's equation we also derived that for a very specific situation where the flow is continuous, streamlined, as in laminar, incompressible, non-viscous, irrotational. In that kind of a situation, we came up with what is known as the Bernoulli's equation. So in the Bernoulli's equation, you have that the pressure at any given point in time plus rho gh, h being the vertical height, rho being the density, g being the acceleration due to gravity, p being the pressure, plus half rho v square, v being the velocity, is equal to a constant. Okay, this is something that we'll be using. All right. Okay, so from the Bernoulli's equation we can come up with what is the very famously known as the Bernoulli's theorem. Okay, so to understand the Bernoulli's theorem, let us look at a particular case of horizontal fluid flow. So let's suppose that there is some sort of a tube or a pipe or a some sort of a cavity through which fluid is in motion. There is a streamlined flow of an incompressible fluid happening continuously. So let us draw the diagram first. Something like this. So this is the opening of the pipe, this is the exit. Okay, and there is fluid which is traveling through it. Okay. Okay, there are various streamlines going through it, you know. Okay, these are various streamlines of the particles in the fluid going from the entry to the exit. All right, in that kind of a situation, we have already looked at the continuity equation, but let us apply the Bernoulli's equation in this kind of a situation. So let's suppose that this, so when there's the at the point of entry, I call it this particular streamline to be point 1, and on the point of exit for the same streamline I call it to be point number 2. Okay, so if I apply the Bernoulli's equation in this kind of a fluid flow, then I can say that according to Bernoulli's equation, the static pressure at point 1 plus the gravitational pressure rho 1 g h1 plus the kinetic pressure rho v1 square is equal to p2 plus rho 2 g h2 plus half rho 2 v2 square. Now, because we are dealing with incompressible fluids, so Bernoulli's equation deals with incompressible fluids at points P1 and 2. Therefore, rho 1 is equal to rho 2, first of all. Second of all, if you look at the nature of this fluid flow, it has a certain kind of symmetry with respect to the horizontal. So if I look at the streamline at the very middle, there is an equal amount of streamlines above it and equal amount of streamlines below it. Okay, so in this kind of a situation, what we do is we approximate by saying that there is no change in the gravitational pressure from point 1 to point 2. So what we say is that rho 1 gh1 is equal to rho 2 gh2. The reason we do that is because, first of all, if you look at one individual streamline, which is this one, if you look at this individual streamline, of course there is no change in height. But if you look at the other streamlines, for every streamline that is above this, there is also a streamline that's below it. For every streamline that is above it, there is also a streamline that is below it. So that means if you look at this streamline, there is a decrease in height over a period of this motion. Similarly, for this streamline, there is an increase in height over the period of this motion. So there is an equal amount of height compensation that takes place based on both these two regions. So if I divide the entire region by some horizontal axis, there is an equal amount of streamlines above it, which decreases by a particular height, and there's an equal number of streamlines below it, which increases in a particular height. So what essentially happens is that these two quantities cancel out and they do not contribute to the equation. Are you able to understand this? So the gain in the potential energy because of the streamlines below it, and the loss in the potential energy due to the decrease in the height of the streamlines above it is equal because of the symmetry with respect to horizontal axis. Are you following?
Yes, sir.
So therefore, I can cancel out these two terms. All right. So I can cancel out these two terms because of there's a certain symmetry to this horizontal flow. The amount of potential energy, gravitational potential energy that is being gained and lost is exactly equal. So we cancel out these two terms. So all that we are left with is I can say that P1 minus P2 is equal to half rho I am going to take as common because it's an incompressible fluid, and you have V2 square minus V1 square. So essentially we get the pressure difference between point 1 and point 2. So here there are two things that are different. So there is a particular velocity here. So velocity is, let's suppose, V1. Here the fluid has a certain velocity V2. Here the fluid experiences a particular pressure P1. Here the fluid experiences a particular pressure P2. So as you can see, can anybody tell me where the velocity would be greater, 1 or 2?
2.
2 will be greater because that comes from the continuity equation. So if I apply the continuity equation, So continuity equation for the incompressible fluids essentially tells us that A1 V1 is equal to A2 V2. Since A2 is smaller than A1, the exit area of cross section is smaller than the entry area of cross section. Therefore, V2 is greater than V1. Now, if V2 is greater than V1, what does this mean for our equation here? So, if V2 is greater than V1, it automatically implies that P1 is greater than P2. Do you follow?
Yes, sir.
So as the streamline goes from 1 to 2, there is an increase in velocity, but a decrease in pressure. Okay, so here I can say that velocity is more, and here velocity is less, but here I can say the pressure is less and pressure is more. Okay, so if you look at horizontal flow of a streamline, then increase in velocity is associated with a decrease in pressure, and a decrease in pressure is associated with an increase in velocity, and vice versa. Are you following this conclusion? Conclusion.
Yes, sir.
So the conclusion is very simple. During horizontal flow of a streamline, an increase in velocity or speed, I can say whatever you want, because I'm not dealing with vectors. Speed is accompanied by a decrease in pressure. Okay. Now this is true for this in general individual case, but in fact it is true in various different circumstances also. So whenever we look at the speeds of a fluid in the vicinity of each other, then the fluid region that is associated with greater speeds is always associated with lesser pressure compared to the area of the fluid that is associated with lesser velocity, which is associated with more pressure. In fact, this simple idea is given the name of what is called the Bernoulli's theorem, okay, or Bernoulli's principle.
Sir, would you please explain that gravitational pressure term cancelling again?
So if you look at one streamline here, there is a streamline that is associated with a decrease in height, yes?
Yes, sir.
So that is associated with a decrease in the gravitational potential energy, and then there is a streamline that is correspondingly associated with an increase in height.
Yes,
So
sir. Yes.
when you add up all the streamlines, so this is associated with, let's suppose, a decrease in the potential energy, and this is associated with the increase in the potential energy. When you add all of it up, it always comes out to be zero. So therefore, both these sides, they end up becoming zero,
Okay. Yes, sir.
canceling
Got
each
it,
other
sir.
out.
Yes.
So Bernoulli's theorem, okay, or principle.
Sir,
Yes.
sir, if we consider a pipe such that it has same cross section, what I mean that if at V1 and V2 the velocity is same, then sir, by this idea the P1 and P2 will be same. But sir, then how can a liquid flow if it is having same pressure at both the ends?
You mean that there is a pressure difference, right?
Yes, sir. Means
Because of which the flow is happening.
what I mean here is that if I consider the cross section to be same at both the ends, and then by this idea, then by continuity, I will have the same velocity at both the ends. But then
Wait,
that
wait.
means,
Can you slowly repeat the question?
so like if I consider that the cross section is same for both the points, point A and point two, point one and point two, so the velocity will also be same at both the ends. Then then from this equation that P1 minus P2 will turn out to be zero. That means P1 is equal to P2. But sir, if the pressure is equal at both the ends, then how can my liquid flow?
Uh, Liquid can flow because, how do I explain it to you?
So due to inertia.
Yeah, exactly.
Inertia.
Due to inertia, you can think of something. If something is in motion, it will be in motion, right? Are you understanding? If something is already in motion, it will be in motion. The change in the velocity is associated with a change in pressure.
Okay, sir. Got it. Got it.
But if it was already in motion, let's suppose you have a horizontal pipe and there is a motion that was created by some pressure difference initially, but that motion will remain there. But if you look at point 1 to point 2, there is no pressure difference here, but the motion was initially there. But if you want to create a flow of a fluid that is at rest, now there you need to create a pressure difference. So pressure difference in fact acts as some sort of an accelerating kind of a impact. Are you understanding?
Yes, sir. Got it. Thank you, sir.
Okay. So the Bernoulli's theorem, I can in general say that an increase in speed, okay? So it is the increase that is associated with speed. The increase in speed of a fluid occurs simultaneously with the decrease in pressure of the fluid. Decrease in pressure of the fluid. Now this sort of a phenomena, an increase in the speed of the fluid is associated with the decrease in the pressure of the fluid, has some very beautiful applications in our day-to-day life in physics and technology. So let me give you a couple of examples. So first of all, let us look at one example of two boats floating, or how do you call it, moving parallelly near each other. Okay, so let's suppose that there are two boats and in a river. So let's suppose there is a river like this. There's a river and then there are two boats that are traveling, you know. Let's suppose this is boat number 1. ऊपर से देख रहे हैं, this is let's suppose a top view, and this is boat number 2. And what happens is that as both the boats are sort of moving through the river, the water around it has a relative velocity with respect to the boat. So the water around it will flow sideways, you know. So if the boat is moving in this direction, if both the boats are moving, let's suppose this boat is moving in this direction, this boat is moving in this direction, and I look at the water flow, the water will go in this particular direction. It has a relative motion with respect to the boat. Okay, so the water will be going like this. So there will be a couple of streamlines of the water going in this direction, in this particular direction. Similarly, for the other boat also, the water will be traveling in this particular direction, and the water will be traveling in this particular direction. Now, if the boats are sufficiently near enough, what is going to happen is that even if they are moving at same velocities, let's suppose boat A and B are moving at the same velocities, and therefore the streamlines of the river water near its edges are kind of, the relative velocity is same as that of the boat with respect to the ground, what is going to happen is that the velocity of the streamline in this region and this region and this region are not going to be the same. Can anybody tell me what the velocity of the streamline will be higher in which region? Velocity कहाँ ज़्यादा होगा fluid motion का?
बीच में सर.
बीच में होगा ना, because यहाँ पे vector add हो रहा है. There are two streamlines flowing with twice the velocity, so there is a vector addition that happens, because of which the effective velocity will be larger. So velocity is larger here. Velocity of relative velocity, let's suppose relative velocity of streamline is larger compared to the outwards areas. So velocity अगर ज़्यादा है तो फिर pressure क्या होगा यहाँ पे compared to the other side? Pressure will be less. Okay, pressure is less. The pressure is less का मतलब ये है that if there is a pressure of, let's suppose P naught here and pressure of P naught here, यहाँ पे pressure होगा P such that P is less than P naught, because बाहर जो velocity है वो कम है. Because of this region, there will be a force acting in this direction. So both the boats will experience some sort of an attraction towards each other. Are you understanding? Even if they are trying to move in parallel lines, because of the difference in the velocities of the streamlines in between and outside, they will experience a thrust towards each other. So just as velocity the boats are traveling, they will tend to experience a force. The force may be negligible compared to various other factors, but theoretically there will be a force that they experience that brings them together. So it looks like the boats are attracted to each other. Are you understanding?
Yes, sir.
Okay. Now, any other example of Bernoulli's theorem? Any other example of Bernoulli?
Plane.
The lift experienced by the wings of a plane. Okay, we can say aeroplane lift. Now, of course, there are many factors associated with aeroplane lift, but one of the very common factors that is associated with aeroplane lift is provided by the Bernoulli's theorem. So essentially what happens is that, so as the aeroplane starts traveling at very high velocities, okay, before it climbs up, airport track पे it moves at very high speeds ना. कभी आपने अगर एरोप्लेन में ट्रैवल किया होगा तो suddenly it starts traveling at very high speeds that are, you know, comparable to a very fast supercar or something like that. So what happens in that situation? So when an aeroplane is traveling at very, very high speeds, let's suppose in a track, and the body of the aeroplane, you know, does not create any specific lift or anything, but the aeroplane has two large wings by each side, and these wings are constructed in a particular fashion. So the wings have a particular shape, if you have seen, or something like this. Something like this, you know, the wings have some kind of a shape, and the reason of the shape is that they create a structure so that the streamlines that are being created, so there are streamlines here, you know, the streamlines that are being created are created in such a manner because of the shape of the wings of the aeroplane, that the velocity of the streamlines are lesser below the wings. Okay, so here v is lesser compared to above the aeroplane wings, where v is larger. Okay, now this directly corresponds to a pressure difference, in the sense that here P is larger, but here P is lesser. which means that there is a pressure difference that ultimately creates some sort of a thrust upwards. Okay, it creates a thrust upwards, and it is this thrust of the air pressure difference that lifts up the aeroplane. कभी सोचा है कि इतना भारी एरोप्लेन कोई छोटा थोड़ी होता है. आई मीन 10-20 ट्रक के साइज का बराबर होगा ना. ट्रक बाइक इज सो हैवी, बाइक से 5 गुना हैवी है कार से 10 गुना हैवी होगा ट्रक से 50 गुना हैवी होगा एरोप्लेन. एंड सच अ हैवी ऑब्जेक्ट इज लिफ्टेड अप इन एयर, and it is ultimately as a result of the pressure gradient created by the air itself. Okay, so air में जो pressure gradient create होता है, that itself creates lifts up the aeroplane. So it is not something to be ignored. Okay, the pressure difference itself is so huge, spread out over the area or the cross section of the wings, that it lifts up such a heavy object. So without the atmosphere, there cannot be any aeroplane. अगर atmosphere नहीं होता तो aeroplane होगा ही नहीं. The aeroplane only exists because of the air, and the pressure differences that gets created as a result of the velocity differences of the streamlines above and below the aeroplane wings. Is that understood?
Yes, sir.
Now, of course, there is a lot of things here. There are various kinds of drags associated with it. There is a drag of skin contact. कुछ aeroplanes में आपने देखा होगा कि यहाँ पे छोटे छोटे वो कुछ buttons type के होते हैं that tries to create turbulences and vortices. Fluid dynamics is very complicated, okay? Fluid dynamics is extremely complicated. It creates, there are many factors, but this is one of the factors that is responsible for creating some kind of a lift. Can anyone give me any other example?
Magnus effect.
Very good. Magnus effect is a very good example. Whoever loves football कौन देखता है?
मैं खेलता हूँ सर.
खेलते हो तो कभी फ्री किक मारा होगा ना?
हाँ सर.
फ्री किक मारने के टाइम पे बॉल कभी कभी स्विंग कर जाता है. हैव यू नोटिस्ड?
हाँ सर, होता है हर बार.
बॉल स्विंग कर जाता है. ठीक है. अगर एनीबडी नोज देयर वाज अ ग्रेट प्लेयर बाय द नेम ऑफ रोनाल्डिनो, रिवाल्डो, यू नो दीज प्लेयर्स. 10 साल पहले होता था यार.
हाँ सर.
So they were very famous for kind of the banana kick, है ना? जो banana kick होता है, they kick a ball, but the ball goes like this and swings midair and comes and goes into the goal. ऐसा क्यों होता है? जब आप स्पिन करते हैं, क्रिकेट में भी आप क्रिकेट खेलते हैं तो बॉल को स्पिन करते हैं. Of course, there are other factors also, but this is one of the reasons. So what happens is that when a ball, like a football or like cricket ball or something, is traveling through air, okay, let's suppose that is traveling through air. So let's suppose that there is a ball that is traveling through air. Okay, it's a ball that is traveling through air, और ball की जो direction है वो, अच्छा मैंने इधर डायरेक्शन बनाया ना, दोनों का उल्टा बना दिया इस तरफ. इसका डायरेक्शन ये है, बॉल का डायरेक्शन लेट्स सपोज ये मान लेता हूँ. ठीक है. अगर बॉल का डायरेक्शन ये है तो जो स्ट्रीमलाइंस होंगी दे विल बी लाइक दिस. एयर में जो स्ट्रीमलाइंस क्रिएट होगा ना, रिलेटिव वेलोसिटी होगा इनका इस तरह से. Now it's all well and good if the ball has no rotation associated with it. Let's suppose that the ball is associated with some sort of a rotation. Okay, ball has some sort of a rotation that is associated with it. Okay. Ball has a rotation associated with it. आप जब बॉल को किक करते हैं, you kick on the side so that not only it goes forward but it also starts rotating as it goes. तो जैसे जैसे रोटेट करता है तो what happens is that there is at each point, let's suppose here it is rotating with a velocity of omega. So the streamlines are moving in this direction with, let's suppose, a velocity of v. Okay, so the effective velocity of the streamlines in the upward region becomes v plus omega r Okay, and the effective velocity of the streamlines in the lower region, because ball is going like this, streamlines are going like this, the ball velocities are in opposite directions, so this becomes v minus omega r. So essentially there is a change in velocity. So यहाँ पे क्या होगा, velocity is greater. Okay, और यहाँ पे क्या होगा, velocity is lesser. Lesser velocity is associated with what? Greater pressure. So therefore the ball will experience some kind of a push in this direction. So effectively ball क्या होगा, ball will start traveling like this. ये बॉल का जो ट्रैजेक्टरी होगा वो इस तरह से होगा, ना, बॉल का ट्रैजेक्टरी will be something like this. Effective trajectory of the ball. So therefore,
upper side होगा,
pardon,
effective trajectory upper side.
ऊपर की तरफ velocity
Pressure
ज़्यादा
will
हुआ
be
ना.
more than the bottom.
Sorry, I'm
Pressure.
sorry. So velocity is lesser, so pressure is higher. Thank you. And pressure is lesser. Pressure is lesser. Pressure lesser होगा तो effective trajectory इधर होगा. Okay. तो कभी आप फुटबॉल खेलते हैं, इवन जो लोग टेबल टेनिस खेलते हैं, नो, अगर आपने टेबल टेनिस खेला होगा तो वो बैट लेकर के स्विंग करते हैं बॉल को, they give it a rotation. Because of that rotation, not only the ball swings mid air, but वो drop करने के बाद it has a particular trajectory which is not straightforward. Okay, drop करने के बाद it is a particular trajectory. So it is associated with, basically these kind of tricks are associated with all these sports where the ball is involved, that can create rotation mid air and as well as change the direction after it bounces. So these are all examples of classic examples of what is known as the Bernoulli's theorem, that whenever there is a fluid motion, then that fluid motion is the nearby vicinities are associated with a difference in velocity. They will also be associated with difference in pressure, and the pressure is quite large, as you can see that in the aeroplane lift kind of a situation. Okay, one more application of the Bernoulli's principle is the velocity of efflux. Okay, let us look at the, okay. कभी कोई जो टैंकर होता है या पानी का कोई टैंक होता है, आप एक बात बताइए, अगर मैं पानी का एक टैंक है पूरा भरा हुआ है और मैं 3 होल्स क्रिएट करता हूँ, एक ऊपर, एक बीच में, एक नीचे, तो कौन से होल में जो पानी निकलेगा विल हैव अ ग्रेटर वेलोसिटी? लोअर. व्हाई?
प्रेशर एक्स्ट्रा हो,
वहाँ प्रेशर ज़्यादा है तो वेलोसिटी ज़्यादा होगी. So essentially that is what's happening. So let's suppose that there is some kind of a container having some sort of a fluid. Okay, so if I draw, let's suppose I exit here and exit here and exit here. So this is associated with a some kind of a motion like this. This is associated with some kind of a motion like this. This is associated with some kind of a motion like this. Okay, so यहाँ पे जो है, you have a particular v, particular v, particular v. Now effectively what is happening is that this also comes as a consequence of the Bernoulli's principle only. It's just that if you look at the Bernoulli's equation, just inside and outside a exit, Okay, so if I take, let's suppose this particular situation, if I take this scenario, if I take this particular scenario, and this comes out with a velocity of v, let's suppose, all right, and there is a pressure that is created due to a volume of water having here. So essentially the half rho v square, which is outside, is created by a pressure of gravitational pressure of rho g h. All right, there is a static pressure, there is an air pressure, वो दोनों के side cancel हो जाएगा. There is going to be a gravitational pressure inside because of all the water that is inside above it, and there is going to be a, यहाँ पे velocity ज़्यादा नहीं होगा अंदर exit के अंदर, but exit के बाहर they will have a specific velocity. So from here you can see that v square is equal to twice gh. So this is a formula for the velocity of a efflux, also known as v is directly proportional to root over h. Okay, so जैसे जैसे height, जैसे जैसे depth बढ़ता जाएगा, sorry I define h here as the depth. So जैसे जैसे depth बढ़ता जाएगा वैसे वैसे velocity increase होगा. With increase in depth, speed of the flow at exit will be larger. Will be greater. All right, so these are some of the concepts associated with the Bernoulli's theorem. Let me give you a couple of questions so that thoda sa you'll get a little bit of a idea of how to solve problems. ठीक है, मैं कुछ problems दूँ आपको?
Sir,
Yes.
sir, can you explain again how you got rho gh equal to half rho v square? Like, is it a conservation of energy?
This is actually conservation of energy principle. You see the entire pressure here. So there are two pressures here. Okay, so there is the pressure of the P naught, which is the air pressure. So this is the pressure that is experienced by both this thing here and here also. But there is also a pressure due to the weight of the liquid above it, which doesn't exist on the other side. Okay, so because of this term arises, the first term arises, but there is no velocity here. So I can say that there is half rho 0 square, but there is a velocity after the exit because the water starts flowing at a particular velocity outside, but just inside the velocity is not that high or negligible at all. So therefore मैंने P naught लिखा नहीं, P naught is equal on both sides, and दूसरा term भी लिखा नहीं. So this is 0, this is 0, this gets cancelled. Effectively, the kinetic energy is coming from the gravitational pressure created by the water of this particular depth. Okay.
Okay, sir, got it.
All right, let me give you a question and then you guys can try it and see. So we'll start with a simple question. Okay, let's start with a simple question. This is a very easy question. It came in JAM 2018. I'll not help you out, okay? I think you should be able to do it. So start this question. I'll start the poll. Okay, I've launched the poll. You can try these two questions. A syringe is used to exert 1.5 atmospheric pressure to release water horizontally. The speed of the water immediately after ejection is what? Take 1 atmospheric pressure to be 10 to the 5 Pascal. Density of water is 10 to the 3. So let me give you a couple of options because I've given you the poll. So 5 meter per second, 7.5 meter per second, 10 meter per second, and 12 meter per second. So एक syringe है. Syringe exerts 1.5 atmospheric pressure. So what is the speed of the water after ejection? Try this question. Ipshita, your answer is correct. Ayush, correct answer. Saeed, correct answer. Durgesh, Akshay, Chetan, Sachin, correct answer. This is a relatively easy question, huh? All right, 5.5 minutes. Deepak, Neetu, Mayank, Sambiti, correct. All right, करने की ज़रूरत है क्या इसको? Seems that all of you have done it. कर देता हूँ मैं जल्दी से. So if you have some sort of a syringe like this, okay, this is a syringe, just creating some kind of a pressure here. Okay, you have this. Okay, so let's suppose this is point A and point B. All right, so a syringe exerts a pressure of 1.5 atmospheric pressure. So let's suppose that at point A and at point B, so we look at the Bernoulli's equation. So PA plus rho is constant, GH same for both, plus half rho VA square is equal to PB plus rho GH plus half rho VB square. तो बाहर क्या प्रेशर होगा? PB. So PB is nothing but the atmospheric pressure. Okay. Atmospheric pressure, because बाहर कोई दूसरा प्रेशर नहीं है. So PA is given as 1.5 PB. Height में कोई differences नहीं है. As you can see that it's horizontal. So if it is horizontal, then it means that there are equal number of streamlines above and below that experiences the rise and the fall in the height. Therefore, both of them will cancel out. So 1.5 PB minus PB is equal to half rho VB square minus VA square. So therefore, डेंसिटी दिया है, सब कुछ दिया है. सो दिस इज नथिंग बट 0.5 PB कितना एटमोस्फेरिक प्रेशर इज इक्वल टू इंटू 10 to the power 5 पास्कल इज इक्वल टू हाफ रो इज इक्वल टू 10 to the power 3. वेलोसिटी VA is near approximately 0, let's suppose, approximately 0. So this is nothing but VB square. So therefore, this becomes VB square is equal to 0.5 into 2 is 1 into 10 to the power 2, or VB is equal to 10 meter per second. This is your answer.
Sir,
Yes.
sir, how VA velocity at point A is nearly zero? I didn't understand.
There is no other way to go about it. Just like in this particular situation, I assume that velocity inside was 0. Therefore, I did not even put the half rho 0 square. So whatever the syringe is, if you look at it, the velocity is very, very less. You just press the button slightly. So the velocity, whatever it is here, is very, very less compared to whatever the velocity is here. Okay, this velocity is quite high. So comparatively, if you have a very small velocity, the square of the velocity term will be negligible.
Okay, sir. Good.
It's a square of the velocity term, which velocity is already less, square term is even smaller. All right. Okay, so I hope you have understood this question. Let me give you one more question. Let me give you one more question. Slightly difficult question, but let me give it to you and see if you can actually do it. Okay, majority have given me the correct answer here. This is a relatively easy question. I'm going to give you a little bit of a difficult question. All right, try this question. I'm not going to explain it too much. See if you can understand it. And to demonstrate Bernoulli's principle, an instructor arranges two circular horizontal plates of radii b, okay, each with distance d, which is this is d. Between them, the upper plate has a hole of radius a. In the middle, on blowing air at a speed of v naught through the hole so that the flow of the air rate is pi a square v naught, it is seen that the lower plate does not fall. If the density of air is rho, the upward force on the lower plate is well approximated by the formula. Assume that the region r less than a does not contribute to the upward force and the speed of the air there is negligible. So what is the upward force? I'm giving you 5-6 minutes. Please try this. Are you able to understand what is happening in the question? क्वेश्चन में क्या हो रहा है, किसी को नहीं समझ आया है?
Sir, please explain it. I'm not getting it.
Okay. So imagine that there are two plates like this. Okay. So this is just a side view, let's suppose. Okay. This is a side view. You know, side view. So, but okay. So या इसको मैं हटा ही देता हूँ पूरी तरीके से. So these are two plates. Okay. So one is this plate. And then there is this one plate. Now what is happening is that what is happening is that there is air that is being thrusted through this particular opening in the above plane, and then this air is exiting outwards. And because of this situation, there is some kind of an upward pressure, upward force acting on the plate. Upward force acting on the plate, because of which the plate does not fall down. Two discs, let's suppose, are on top of each other. The second disc is free to fall, but in the top disc there is a hole in which a particular air is thrusted inwards with a particular velocity, so that the air comes and then flows out, exits. But this situation creates a phenomena of upward thrust. So what is this upward thrust? So if the density of air is at the upward force, that is what they are asking. Is the question clear now?
Yes, sir.
Okay, please try. This came in Jam 2007, huh? 17. The radius of this is A. The radius of this is B. So you're not supposed to consider this region. This region does not contribute to the upward thrust. The other region does. Sandeep, no, that's not correct. Ipshita, yeah, Ipshita, you're correct. Yes, Ipshita, correct. Sandeep, yeah, one of those options. One of those options. Okay, shall I start doing then?
Yes, sir.
Okay. Anybody can tell me what kind of concept we have to use here?
P plus half V squared plus.
Name the concept.
Bernoulli principle.
Bernoulli's principle, yes. That will give us a pressure difference. That will give us a force. Anything else?
Equation of continuity.
Equation of continuity will give us a relationship between the velocities. So velocity of entry, velocity of exit will be connected by the equation of continuity. From the velocity, I apply the Bernoulli's equation. I'll get the pressure difference. From the pressure difference, I'll get the force. Okay. So you use equation of continuity. The equation of continuity will give an idea about the velocity. You apply the velocity in Bernoulli's equation. The Bernoulli's equation will give us an idea about the pressure difference. The pressure difference can be used to calculate the upward force or thrust. That's it. This is the simple concept. So if you look at the entry and the exit, and I apply the equation of continuity, so equation of continuity basically tells us about, the area of cross section and the velocities associated with the fluid flow in and out. So equation of continuity. What is the equation of continuity? The equation of continuity simply says the area of cross section 1, V1 is equal to area of cross section 2, V2. What is the velocity at the entry? It is given as V0. What is the area of cross section of entry?
Pi a square.
Pi a square. Very good, very good. Let's suppose the velocity at exit is V. What is the area of cross section of the exit?
Twice pi x.
2 pi b t.
2 pi b d. Yes?
Yes, sir.
2 pi b is the circumference of the disk and d is the gap. So the entire area of cross section is in fact a cylindrical surface. Okay, the area of cross section associated with the exit is a cylindrical surface. The base circumference is 2 pi b and the height is d. So 2 pi b d you can say. But I'm not going to use b here, because what you will see is ultimately that there is a particular radius that is not contributing to the thrust. That is this small. So this region not contributing to thrust. Okay, because यहाँ पे जो है, यहाँ पे कोई velocity नहीं होता है horizontal direction में. यहाँ पे सिर्फ vertical direction में velocity है and horizontal direction में कोई velocity नहीं है. That is what we are concerned with. Question में already दिया हुआ है that assume that the region with r less than a does not contribute to the upward force. तो इसलिए does not contribute to thrust. So what I'm going to do is I'm not going to take b here because b is changing. Okay, so the r less than a, I'm not going to that is not going to contribute to the force equation. R greater than a but less than b is going to contribute to the force equation. Therefore I'm going to take some just a random disk here. Okay, later on I'll look at the limits. So let's take a random disk having distance of r. Okay, so considering a random plates of radii r. So if considering a random plate of radii r, then that will be equal to 2 pi r here. That is the only difference. Yes, this is clear. Yeah, ye clear hai.
Yes, sir.
The reason I am taking r instead of b is that ultimately I want to include the contribution of the pressure from r greater than a but less than b. Because of this, I am not taking I am taking the r here, okay, not b, because I need to integrate for that particular region. So starting से ही मैं r लेके चल रहा हूँ, बाद में उसको मैं substitute कर दूंगा जैसे मुझे substitute करना है, integrate करना है. So from here I get an idea about the velocity. So velocity is equal to pi a square v naught upon,
वो लेस देन ए वाला समझ में.
अरे यहाँ पे ये जो लेस देन ए वाला रीजन है, इट डज नॉट, दिस रीजन डज नॉट कंट्रीब्यूट टू द अपवर्ड थ्रस्ट. या
यस
सो देयरफॉर मैं स्टार्टिंग से ही जो है एक रैंडम डिस्क लेके चल रहा हूँ. मैंने इसको b इज इक्वल टू आर सब्सटीट्यूट नहीं किया है. बेसिकली मुझे जब मैं फोर्स कैलकुलेट करूंगा तो मुझे इस रीजन के लिए फोर्स कैलकुलेट करना है, इस रीजन के लिए, और r लेस देन a के लिए नहीं करना है. तो बेसिकली मुझे a से लेके b तक इंटीग्रेट करना पड़ेगा. तो मैं स्टार्टिंग बाद में सब्सटीट्यूट करने से अच्छा मैं स्टार्टिंग से ही उसको r लेके चल रहा हूँ.
ओके सर, गॉट इट.
स्टार्टिंग से ही मैं इसको r लेके चल रहा हूँ, नहीं तो बाद में मैं सब्सटीट्यूट कर सकता था, कोई दिक्कत नहीं है, बट आई एम स्टार्टिंग से ही मैं r लेके चल रहा हूँ. ठीक है, b के जगह पे r लिख दिया मैंने, इसको हटा दो यहाँ पे. Okay, so therefore the velocity is equal to, तो pi और pi यहाँ पे हो गए cancel. This is equal to, velocity is equal to a square v naught upon 2 r d. Fine. So equation of continuity से हमें मिल गया velocity. Now velocity से हम Bernoulli's equation पे आते हैं. Let's come to the Bernoulli's equation. तो Bernoulli's equation अगर आप इस चीज को देखेंगे तो you see that there is a air flow here, and then there is an air flow here, and then there is air here also. यहाँ पे भी air है, but the only difference is that the air here is static. Okay, there is zero velocity in the fluid here, but there is a velocity vector in the fluids here. So this is a surface just like हमने अभी aeroplane की बात करी थी, that there is a plane wings, there is a velocity difference up above and below the wings that results in a pressure difference. So that same thing is happening here, that there's a plate, but there is a flow of air above the plate and no flow of air below the plate. So there's a velocity difference above and below the plate. So that results in some upward or downward force. So this pressure difference will create, तो velocity ऊपर ज़्यादा है, नीचे zero है, तो प्रेशर ऊपर कम होगा, प्रेशर नीचे ज़्यादा होगा. तो इसकी वजह से जो है एक अपवर्ड थ्रस्ट क्रिएट होगा. आर यू अंडरस्टैंडिंग द कॉन्सेप्ट ऑफ व्हाई इट इज नॉट फॉलिंग डाउन?
Yes, sir.
Okay, so I want to calculate that pressure difference. The only way I can calculate the pressure difference is using the Bernoulli's equation. So let us look at these two scenarios of a layer of fluid above the plate and a layer of fluid below the plate. So if you look at this, so if I calculate it, let's suppose I call this as 1, I call this as 2. Okay, so P1 plus rho g h plus half rho v1 square is equal to P2 plus rho g h plus half rho v2 square. Now v2 is 0. Okay, because नीचे जो है, नीचे कोई फ्लूइड का फ्लो नहीं हो रहा है as far as we are told in the question. So v2 is 0. Rho gh and rho gh will get cancelled out, because if I look at very infinitesimal layer of a fluid above and below it, there is not much difference in the gravitational pressure. The only difference, even if there is, it's very negligible compared to the difference that arises out of the v square term. So therefore velocity कहाँ ज़्यादा है? v1 में velocity ज़्यादा है. So I'm going to write this as so P2 minus P1 is equal to half rho v square. So v square मतलब ये basically ये v square is v. Okay, v1 is equal to v. nothing else. So therefore the pressure difference comes from half rho v square. So if I substitute this here, then I simply end up getting half rho v square is a to the power 4 v naught square upon 4 r square d square. So therefore the pressure difference comes out to be rho a to the power 4 v naught square 8 r square d square. Okay, so this is the pressure difference, but we are interested in calculating the force, upward force. So what is the relationship between pressure and force? So force associated with this pressure difference is equal to, so del F can be written as del P. So अगर मैं disk को दोबारा से बनाता हूँ, if I look at the disk, what is happening is that there is a pressure at every point in the area of the disk apart from this. Okay, so if I create a random ring, okay, if I create a random ring of a particular, you know, sort of a width, then there is a force acting on that. Okay, so एक random ring के ऊपर जो pressure difference है, it is acting over an area of 2 pi r dr. Yes, if I create a random ring out of the entire disk, then that ring has a width of dr, then it contributes to an area of 2 pi r dr. So the pressure difference multiplied by that area is equal to the force on that particular ring. Yes?
Yes, sir.
So therefore this simply becomes rho a to the power 4 v naught square upon 8 r square d square into 2 pi r dr. So r square and the r gets cancelled, and if we are interested in calculating the total force, then the total force is essentially therefore nothing but F is equal to rho a to the power 4 v naught square pi 2 से यहाँ पे हो गया 4 r d square dr. You have to integrate it from where to where. What is the area that is contributing to this force?
The radius greater than a and till b.
So we can integrate it from a to b. Yes.
Yes, sir.
So there इसीलिए मैंने r लिया था. We integrate it from r is equal to a to r is equal to b, because this is the area that is actually contributing to the pressure as according to the question. So this is equal to pi rho a to the power 4 v naught square upon 4 d square integration of dr upon r. So this is a to b. So this is equal to pi rho a to the power 4 v naught square 4 d square ln of b upon a. So this is your answer. So this is the force pi rho a to the power 4 v naught square by 4 d square ln ba. So pi rho v naught square to the power 4 upon 4 d square ln ba. This is the answer to this question.
Sir, what do they mean by flow rate in the question, sir?
Flow rate is the कहाँ पे लिखा है एक सेकंड. हाँ, flow rate is basically this quantity ना. ये this is the flow rate ना. If you remember my earlier derivation from yesterday, let me show you. From yesterday when I was deriving the continuity equation, so I took this as this is the flow rate, rate of mass per unit time entering or exiting.
Okay, sir.
तो यहाँ पे मैंने m को कैसे लिखा था? m को लिखा था डेंसिटी मल्टीप्लाइड बाय वॉल्यूम, फिर वॉल्यूम को लिखा था एरिया मल्टीप्लाइड बाय द डिस्टेंस, और फिर जाकर इसको लिखा था कि रो a1 v1 del t1. So flow rate is essentially equal to rho a v. For, you know, if density is constant, I can just write it as rho a v. So basically flow rate is, फ्लो रेट तुम्हारा है वो मैंने क्वेश्चन में लिया ही है ना ऑलरेडी, पाई ए स्क्वायर वी नॉट. पाई ए स्क्वायर वी नॉट. हाँ, सो दिस इज नथिंग बट द dm अपॉन dt टर्म. ओके, दिस इज द फ्लो रेट. ओके, ये क्वेश्चन समझ में आ गया? एवरीबडी इज कंफर्टेबल विद द कॉन्सेप्ट इन दिस क्वेश्चन?
यस सर.
Yes, sir.
All right, we don't have much time, so let us do one more question then. So 4 of you actually gave the correct answer. Very good. So Mayank, Sachin gave the correct answer. Ipshita and Sandeep also. Okay, I'm going to give you not too much time, maybe 2-3 minutes to try this question. ओके थोड़ा सा क्लास को एक्सटेंड करेंगे तो आई थिंक कोई दिक्कत नहीं है ना 5-10 मिनट तो ये
No,
आप
sir.
इसको हाँ तो आप इसको ट्राई कीजिए एक बार सोचिए कि ऐसे कैसे करना है कर सकते हैं कि नहीं एंड देन आई विल हेल्प यू आउट it's based on a very simple concept nothing it's not as difficult as this question that we just now did in fact it's easier so the question says that an incompressible non-viscous fluid is injected into a conical pipe. So essentially this is actually a pipe, okay? The diagram is not very clear, but this is a conical pipe. It's a conical pipe. So there is a liquid or fluid that is inserted into this conical pipe. Injected into a conical pipe at its orifice as shown in the figure, the pressure at the orifice of area A0, pressure at area A0 is P0. Okay, so pressure is, area is A0, pressure is P0. Neglecting the effect of gravity and assuming streamline flow, which of the following plots correctly predicts the pressure along the axis? The axis के along pressure का जो change है, which of the graph denotes correctly? It's a question from JAM 2016. Try it once. Saeed, it's not correct. Chetan, not correct. Sachin, not correct. Kauship, you have the correct answer. Nihar, not correct. Ayush, not correct. Ipshita, you have the correct answer. Ankit, not correct. Sandeep, not correct. Okay, it's been 4.5 minutes. Shall we try? Shall we try?
Yes, sir.
Yes, sir.
Okay. The first obvious concept that we can use is the equation of continuity, right? That means whatever the velocity here, v naught, whatever the velocity here, v naught, and whatever the velocity here, v, is associated with the, let's suppose, area of cross section A. Okay. So if I use equation of continuity, I'll take at least 10 minutes more. Okay, don't worry. This question and one more question I want to do. I can say that A naught V naught is equal to A V. Okay, so therefore I can say that what is V? V is equal to A naught V naught upon A. So what is A naught? A naught is equal to it's not given in the question, A naught, and V naught is also not given in the question, but A is equal to, let's suppose this area is, this radius is R. Okay, now this angle is given to us, so 10 pi by 4 is equal to how much? R upon X. So what is 10 pi by 4?
1.
So therefore R is equal to X. R is equal to X. So if R is equal to X, I can say that pi R square essentially is nothing but V is equal to A naught V naught upon pi X square. So I essentially came up with a relationship of velocity from the continuity equation. Yes? Ye clear hai?
Yes, sir.
Okay, but now I want to associate that change in velocity with pressure. So if I want to apply, I get an idea about the pressure difference, I need to apply the Bernoulli's equation. So Bernoulli's equation at point 0 and let's suppose some random point. Let's suppose here the pressure is P naught plus gravitational, I will not consider because that's a equal. If you look at it, it's symmetrical with respect to the horizontal axis. Therefore, the gravitational term will cancel out on both sides. So half of rho V naught square is equal to whatever the pressure is here plus half of rho V square. So therefore, essentially the pressure is equal to P naught plus half of rho V naught square minus V square. Okay, so what is V? V I have already obtained. So if I apply the V here, P naught plus half of rho, so V naught is, I know what V naught is. V is equal to A naught square, V naught है ना, sorry, V naught है, A naught square V naught square upon pi square x to the power 4. Okay, so therefore the pressure at any given point x comes out to be P naught, some constant, plus half of rho V naught square, which is the initial velocity, 1 minus A naught square upon pi square x to the power 4. So A naught is a constant, pi is a constant. So let's suppose I call it some kind of a constant upon x to the power 4. This equation is clear. So this is actually the mathematical solution to a problem. Yahan tak clear hai beta?
Yes, sir.
Yes, sir.
Now, what is obvious from this solution is that it's an increase. A plus hai na ye plus hai na. So it's an increase from P naught. So therefore, this is not true. This is not true. The only two options are this and this. So the question is, if you can actually check it with a graph, or you can actually do some kind of a trial and error. Agar aap graph mein dekhenge, if you look at an equation of the form, let's suppose 1 minus 1 by x to the power 4, okay, is equal to y. Let's suppose if I plot this, graph, you see this graph, you see this, it starts with some, of course the constants are going to contribute, but it is going to something like this, going to be something like this. Okay, so the correct option is option number A. But you can check whether or not this is true or not. Like for example, at x is equal to x naught, if I substitute in this expression, so if I substitute in this equation, I'll get p is equal to p naught plus half rho v naught square 1 minus a naught is equal to pi a square, sorry, pi x naught square और पाई स्क्वायर एक्स नॉट टू द पावर 4 एंड यहाँ पे पाई स्क्वायर एक्स नॉट टू द पावर 4. So this will give us p naught plus half rho p naught square 1 minus 1. So this is equal to 0. So this is nothing but p naught, okay, which essentially is true for here and here. Alright, लेकिन इसके बाद क्या है, if I consider some point, let's suppose x is equal to twice x naught, अगर मैं twice x naught consider करता हूँ तो p is equal to p naught plus half of rho v square 1 minus यहाँ पे क्या आएगा, यहाँ पे आएगा a naught की जगह पे pi x naught to the power 4 और यहाँ पे pi square x naught to the power, यहाँ पे आएगा pi square x naught की जगह पे 2x naught, सॉरी x के जगह पे 2x naught. So 2 to the power 4 कितना होता है 16, तो यहाँ पे आ जाएगा 16 pi square x naught to the power 4. So this is equal to p naught plus half rho v square into 16 minus 1, 15 upon 16. Can you see this? Do you see this?
Yes, sir.
So what can you conclude from here? What can you conclude from here? What you can conclude from here is that this is not the equation of a straight line. I mean, you can also look at x is equal to 3x naught. If you do this, then you will find p is equal to p naught plus half rho v square 1 minus pi square x naught to the power 4 upon 3 to the power 4 कितना होता है 81 pi square x naught to the power 4. So this is equal to p naught plus half rho v square. What is this? 80 upon 81. You see the slope is not the same. Can you see this? So this clearly is not the equation of a straight line. Is it clear? So एग्जाम में तो आपके पास कोई ग्राफिंग टूल होगा नहीं ना, तो यहाँ से आप कंक्लूड कर सकते हैं दिस इज नॉट द करेक्ट ऑप्शन, दिस इज द ओनली करेक्ट ऑप्शन लेफ्ट. In fact, it's also true from the fact that it's an x to the power 4 term. So x to the power 4 माइनस होके आ रहा है, तो आफ्टर सम टाइम एक सैचुरेशन आ जाएगा, ऐसे जाएगा ऊपर फिर एक सैचुरेशन आ जाएगा, बिकॉज यहाँ पे x to the power 4 टर्म है, यहाँ पे वो भी -1 by x to the power 4. So graphically also it's obvious, but graphical tool अगर आपके पास नहीं है तो थोड़ा सा आपको ट्रायल एंड एरर पर्टिकुलर फिक्स पॉइंट्स में देख के आप रिमूव कर सकते हैं. That is not a straight line. It's in fact a term that sort of the greater so 1 minus 1 by x to the power 4 tends to 1, okay, at infinity or something like that. Limit tends to infinities essentially, basically. So as x tends to infinity, so the answer tends to some fixed saturated value. So fixed saturated value का मतलब है कि ये possible ही नहीं है. It's not possible at all. Clear है ये problem?
Yes, sir.
Okay. Let's do one more question. What do you say?
So why this is
Yes,
happening? Here area is increased, then velocity will be decreased, and pressure should be increased.
No, but the velocity also depends upon the continuity equation, na?
Yeah, from
And
there.
from there the area of cross section कैसे कितना इंक्रीज हो रहा है डिक्रीज हो रहा है उसके ऊपर भी तो डिपेंड करेगा ना वेलोसिटी. तो बेसिकली एरिया इंक्रीज हो रहा है डिक्रीज हो रहा है उससे वेलोसिटी पे फर्क पड़ेगा और वेलोसिटी जितना बढ़ेगा या घटेगा उससे प्रेशर पे फर्क पड़ेगा. आर यू अंडरस्टैंडिंग? सो एरिया
Yeah.
इज इंक्रीजिंग, velocity is decreasing, pressure is increasing, but the mathematical function as to how the pressure is increasing depends upon the actual equation.
That's why here pressure should be increased, but this is not happening here.
It is increasing ना, ये आपको दिख रहा है? The graph is like this. The graph is like this actually. It becomes constant after a while. You see this? Graph is like this. You see this? There is an increase initially and then it becomes saturated. The saturation happens because of this particular term. Are you understanding? It's like terminal velocity, you know. Velocity increase होता है but fixed value में आकर के theoretically speaking time tending to infinity पे velocity constant हो जाता है. तो यहाँ पे भी distance tending to infinity पे ये velocity pressure जो है constant हो जाता है. Are you understanding?
Yes.
So it is increasing, but then it becomes saturated, fixed, whatever. Okay. Let me give you one more question. So I'll give you a couple of questions as homework, which is similar to what we have done today. But एक कर लेते हैं before you leave. एक मैं लिख ही देता हूँ. So there is a nozzle like this. There is a nozzle like this with a height of 50 centimeter. So nozzle is in the shape of a truncated cone as shown. The area at the wide end is 25. So this is 25 centimeters square. And the narrow end has an area of 1 centimeter square. Water enters the wide end. यहाँ से water की entry होती है, ठीक है? Water enters the wide end at a rate of 500 grams. So dm upon dt is equal to 500 gram per second. Okay. The height of the nozzle is 50 centimeters and it is kept at a vertical with a wider end at the bottom. The magnitude of pressure difference is how much? So find out del P between both the points. Can you do that? It's a very easy question. There's a conical nozzle, एरिया एग्जिट और एरिया एंट्री और एग्जिट का दिया हुआ है, हाइट दिया हुआ है, रेट एट विच वाटर इज फ्लोइंग इन दिया हुआ है. व्हाट इज द प्रेशर डिफरेंस एट बोथ द पॉइंट बिटवीन बोथ द पॉइंट्स? दिस इज बाय द वे क्वेश्चन फ्रॉम जैम 2015. Just write down the answer. A very straightforward question. Give me the answer in kilopascal. So 1 kilopascal is equal to 10 to the power 3 Newton per meter square. This is flow rate. Keshav, your answer is not correct. So use the SI units to convert everything to meters and kgs, and use 1 kilopascal is equal to 10 to the power 3. So give me the answer in kilopascal. Question is same as before, you just have to find the pressure difference. Pressure difference can be found out by velocity. Velocity can be found out from area. Ipshita, your answer is correct. Very good. Okay, shall I give you a hint or maybe do the question? Let me do it. Okay. मैंने अभी थोड़ी देर पहले क्या बताया था? I said that flow rate is equal to dm upon dt is equal to how much? So d by dt of m कितना होता है? M is nothing but density multiplied by volume. Okay. So d by dt of density multiplied by volume. Volume मतलब क्या होता है? Area of cross section multiplied by length. So अगर किसी एक पर्टिकुलर पॉइंट पे डेंसिटी फिक्स्ड है, एरिया ऑफ क्रॉस सेक्शन फिक्स्ड है, the vertical distance, infinitesimal vertical distance upon time, इसका एक्सप्रेशन क्या हो जाएगा? ये क्या होगा? रो ए वी होगा ना, इनफाइनाइट वर्टिकल डिस्टेंस अपॉन टाइम, तो ये रो ए वी हो जाएगा ना. सो डी एम अपॉन डी टी इज नथिंग बट रो ए वी. यस
Yes, sir.
So from here I can say that v is equal to 1 upon rho a dm upon dt. Yes, I can use this as a formula in fact, because this is standard from the equation of continuity. So if I apply the Bernoulli's equation, so if I say p1 plus rho g, let's suppose I take this as a reference. Okay, I take this as a reference. If I take this as a reference, तो rho g 0 लिख देता हूँ मैं यहाँ पे, प्लस हाफ रो v1 स्क्वायर इज इक्वल टू p2 प्लस रो g, यहाँ पे h हो जाएगा, प्लस हाफ रो v2 स्क्वायर. सो दिस इज इक्वल टू हाउ मच? मुझे क्या फाइंड आउट करना? प्रेशर डिफरेंस फाइंड आउट करना. प्रेशर डिफरेंस फाइंड आउट करने के लिए आई विल से p1 minus p2. Okay, so p1 minus p2 is equal to rho half rho v2 square minus half rho v1 square. So what is half rho? What is v2? V2 is nothing but 1 upon rho a2 dm upon dt square और यहाँ पे एक रो जी एच भी है, रो जी एच प्लस नहीं माइनस हाफ रो. What is this? This is nothing but 1 upon rho A1 dm upon dt. तो ये एंट्री में या एग्जिट में स्क्वायर प्लस रो जी एच. तो ये क्वांटिटी कितना है? ये क्वांटिटी तुम्हें दिया हुआ है, इट इज 500 ग्राम पर सेकेंड. ये क्वांटिटी भी एग्जैक्टली सेम ही होगा कंजर्वेशन ऑफ मास की वजह से, सिर्फ एरिया अलग अलग होगा, A2 और A1 अलग अलग होगा. ओके, सो दिस इज गिवन एज 5.5 kg per second and this is also 0.5 kg per second. Okay, रो जो है, रो आप लोगे क्या इसमें? रो यू कैन टेक एज 10 to the power 3 क्वेश्चन में दिया हुआ है क्या रो? Whenever you take water के लिए डेंसिटी you can take as for water, you can take density as rho is equal to 10 to the power 3 kg per meter cube. Okay, if you substitute all the values, then the answer that you should get is 17.48 kilopascal. Substitute the values here. In this equation, हाइट में यहाँ पे 50 आ जाएगा, कितना है 0.5 मीटर आ जाएगा, यहाँ पे 0.5 मीटर आ जाएगा. बाकी सारा आप सब्स्टिट्यूट करेंगे तो यू शुड गेट दिस आंसर. Sambiti also got the same answer. Kaushik, you didn't get it again. Okay. So this is a simple straightforward question, just like the other two questions. It's just that applying some sort of a substitution based on what you know, you either use the equation of continuity. I gave this question because here you can substitute this expression in the Bernoulli's equation and come up with a pressure difference. So majority of the questions are kind of similar to each other. I'll give you a couple of homeworks also. इस PDF को आज मैं थोड़ा सा लेट शेयर करूँगा, कुछ homeworks में include कर दूँगा. Questions are not very difficult. They either rely on continuity equation or Bernoulli's equation, or maybe something that comes as a result of connecting these concepts. But ultimately, they will give you the answer. All right. Okay. Is this clear, guys?
Yes, sir.
All right, so I'll give you a couple of homeworks and you try those questions. If you still do not feel comfortable, then we may do some practice session, but that is all for today. I'll see you tomorrow then. Have a nice evening, guys. Good night.
Thank you, sir. Good night, sir.
Bye.